Hey everybody, this is Mr. Hartzler. I wanted to show you today how to solve a truss problem. I don't know that we're going to do the whole thing because it's a really long video that way, but I want us to get through the first couple of steps and then do a couple of our joints so you can kind of see how all of this works. And this is the truss we're going to start with right here. I have some dimensions on here so I know that this is 10 feet over, and I'm not a good artist so you have to kind of bear with me, but that we're going to say is right underneath that D value or that D joint. And the 7.5 is going to be from that straight down, that perpendicular from A to B. C 7.5 is from that little perpendicular spot over to B, and it's the same thing on this side. So we're essentially mirrored this left side with our right side, and we are 10 tall. We only really need those when we go to try and find all of these angles. But we have two reaction forces at joint A. That's because we originally had a pinned connection there. And we have one reactionary force at C because there was a roller connection there. The roller connections only restrict me in one axis, while pins restrict me in two. And you see we have three external forces acting on it. We have 500 at D, 375 at E, and 250 at B. Alright, so we first go through this by trying to figure out if the whole problem is statically determinate. So I determine if it's statically determinate. Let me get rid of that one. By using this formula, 2 times the number of my joints equals my members plus my reaction forces. So how many joints do I have? I have one at each of these letters. So I have 5. So I have 2 times 5 equals the number of members. 1, 2, 3, 4, 5, 6, 7. 7 members, and I have 3 reaction forces. I get 2 from my pin, and I get 1 from my roller. Gives me a total of 3. 10 equals 10, so yes, in fact, it is statically determinate, and I can continue to solve it mathematically. Alright, so let's get rid of that one. When solving trusses, next thing we're going to go into is our external forces. So let me zoom in a little bit here. Okay, let me zoom in that way for some reason. Let me move my little tripod thing around a little bit. Alright, that looks pretty good. See if I can get it to focus a little better. There we go. Some of my forces in my x-axis. So that's where I've got to look back at my pretty picture. And I have my x-axis. I have reaction at joint A in my x-axis, and that's it. Notice all the other arrows are pointing up or down. So I only have one. I have my reaction at joint A in my x-axis. Adding them all up, that's the only one. It must equal 0. Awesome. That one's done. I suggest as you go through, you label those. So this one, I'm not going to write that is a 0. Then I go on and I look at my forces in my y. There's a whole bunch of them. Sorry, I have to keep shuffling papers around here. I have my reaction at A in my y-axis. I have the 500 up here, 250 here, 375 here, and my reaction at joint C in my y-axis. So that's a whole lot of them. Let's list those out. I have my reaction at joint A, my y-axis. I have the 500 that was coming down. I have this 500 coming down. Since it's going negative, it's going down, I need to make sure I have that negative. At joint B, I have a 250 going down. Since it's going down, it's a negative. At joint E, I have 375 going down. Since it's going down, it's negative. And then at joint C, I have my reaction in my y-axis. Since it's going up, or at least I'm assuming it's going up, we assume it goes up until we find out otherwise, and then we'll change the direction of our arrow. But because I'm assuming this direction, I'm assuming it's a positive value. If we end up solving for it and it's negative, that just means I drew my arrow in the wrong direction. Alright, all of those add up to get me 0. They must. Otherwise, my bridge is either rising or sinking. So let's combine our like terms. I have a negative 500 minus 250 more minus 375. So my reaction at A and my Y, and my reaction at C and my Y, and then minus a 1,125 must equal 0. But I can't continue. I have two variables. Well, I suppose I could add over this 1125. But then that's it. RAY plus RCY equals 1125. But that's it. I can't go any further. That's where, and this is a little sloppy, sorry about that. That's not much better. But now I have to find my moments. The sum of my moments must also equal 0. Moments are turning forces. So anything that's going to act on this bridge, not bridge, the truss, to make it spin. We have to assume one point is fixed. I'm going to assume that that is A. So A is fixed. This 500, that makes it want to spin clockwise. So that's a negative moment happening there. I have to multiply it by its distance away. B, that's 250. It's happening negative because it's a clockwise moment. It's pulling me down. That's going to be times 17.5. At joint E, we have 375. And that's going down, so it's a negative moment. And then my reaction at joint C in my y-axis, that's going to be a positive moment because I'm assuming it's going up. So let's put all of that together here on my moments paper. Alright, so at D, that's going to have 500 pounds going down, so it's negative. And it is located 10 away from A. That's my fixed point that I assumed isn't spinning, but everything's spinning around that point. Then over there at B, I have a negative 250 because it's going down. That is 17.5 away. At E, I have a negative 375 because it's going down, or making the whole thing spin clockwise. And that one is 25 away. And then my last one, RCY, that's my reaction force. I don't know what it is yet. And it is 35 away. 35 away, yep. And all of that must equal 0. Good thing is, only one variable. So I'm going to actually type all of that into my handy dandy little calculator. Negative 500 times 10, well that's negative 5,000 minus 250 times 17.5. Alright, all of that gets me a negative 18,750. I still have a positive 35 RCY. Excuse me. Now I need to keep solving for RCY, so I'm going to add that over and divide by 35. And RCY equals 535.714. That's my reaction at joint C in my y-axis. Awesome. We can keep going. We can find the rest of it. I can use that, plug it in up here, and I can solve for RAY. Oh, well, I should say this too. When we added that over, since I added this over, it became positive. Dividing by positive left me positive. If my answer comes out positive, I assumed correctly in the direction of my arrow. So this is, in fact, going up. Alright, let's come back up here and find this one. RAY plus this force I found, 535.714 equals 1125. Nope. And we get RAY as 589.286. I should have all my reaction forces now. I'm going to update them on my paper. RAY we found out to be 589.286. RCY 535.714. I really suggest that you keep updating this as you go. So now you know all of your reaction forces and everything acting on your truss externally. Awesome. Now we have to go through and find out some of our angles. There we are. A lot of this truss is symmetrical. I kind of said that in the beginning. So let's just solve a couple of our triangles, find the angles, and we can keep going from there. Zoom in just a touch here. Alright, that's all it's going to give me. So I want to find this angle, this little one in the bottom right corner by A. I'm going to use tangent because I know SOHCAHTOA, opposite over adjacent. So I know tangent of the angle I'm curious about, this one, equals opposite 10 over adjacent 10. And if you remember anything from any of your trig classes, you know that that must be a 45-degree angle because that's the only place tangent equals 1. You also maybe know that because both my legs are the same, then both my angles must also be the same. That's a little bit of geometry in there for you. Alright, now this one over here. That one's going to be a little tricky. A little bit more tricky, I guess. Not tricky. But tangent, let's do the one at B. Equals opposite over adjacent. And then I have to get theta by itself. So theta equals, this is where we have to use arctan or inverse tangent, 10 over 7.5. So that's on your calculator. That's second. Tan 10 divided by 7.5. End my parenthesis. Oh, I didn't get the decimal in there. 0.5. Enter 53.130 degrees. Oh, sorry, I keep moving that paper around on you. Theta equals 53.130 degrees. Now I can find out my other one. And I'll just write a 53 in there. This other one by 180 minus the other angles I know, which is that one at 53.130 and this one at 90. 180 minus my last angle minus 90, and I know my new angle. My next angle is 36.870 degrees. Awesome. Now I have all my angles. If I happen to want to use this other one up here, I could always do 90 minus that 36.170. Alright, so let's keep trying that. That, just so everybody is clear, I just found the angles in this part of my truss. But the good thing is, this part is the same as this part, it's just mirrored, because it's a very symmetrical truss. Alright. Have my angles. Found my external forces. Let's go look at each specific joint. So, here I'm starting with joint A. I know my reaction at joint A in the y-axis. It's 589.286. My reaction at joint A in my x is 0. I don't know anything else. Oh, I do know this angle. It's a 45-degree angle. Awesome. Let's keep going. Just like we did in the beginning, we have to find the sum of our forces in our x. The sum of our forces in our x-axis must equal 0. And the sum of our forces in our y-axis must equal 0. You only have to do moments the very first time. After you've done it once, you're fine. Let's turn this a little bit. Alright. Okay. Now, I'm going to add up all my forces in my x. I have this one, RAX. Even though I know it's 0, I just want to write it out. I have my vector AB. And I have the x component of AD. AD and my x. Those are my only three things that are acting on the x-axis. They must all equal 0. I know a couple of them. Well, I know one of them. I know RAX is 0. And I know a little bit more about AD in my x-axis. So let's look at that one. I'm going to come down here, and I'm going to draw this just as a regular triangle. AD. Have a 90-degree angle. There we go. And I know that this is the important one. That's AD, the big vector AD. That's important for us. This one down here, that's AD in my x-axis. This one is AD in my y-axis. I really care about this one in the end. I want to find out what AD is, but I'm solving for just the part that is x component of it right now. So I want to solve this piece for ADX. Cosine is going to let me do that. Cosine of my angle, which is 45 degrees, is going to equal adjacent over hypotenuse, so AD in my x-axis, so the AD vector, but just the x component of it, over my regular vector. If I multiply by AD, just the overall vector, that gives me my x component equals the hypotenuse times cosine of 45. Again, I have to use my AD just in my x, but in the end, I'm really looking for the overall vector. So this is what I'm going to substitute into my equation up here. So I don't have to worry about my 0. I have the vector AB, and now instead of just the x component, I'm going to put in the piece that has the overall, my actual vector. And that's my actual vector AD times the cosine of my angle. And those have to add up to be 0. Now I don't know either of these things, so I'm going to have to go and look at my y. Let's list all of the forces acting in our y. My reaction at A in my y-axis, and I have the y component of AD. Those two things must add up to get me 0. Nothing else is applied in the y-axis. Awesome, because this I know is a 589.286 added to my vector. But I know the y component. Similarly to how we found our x component was related to our overall vector times cosine, I'm now going to use sine. So I'm going to also subtract my 589 over. And AD, my y-axis, is going to be my overall AD vector times sine of 45 degrees. That's because I'm looking at the opposite leg over the hypotenuse. So I have to use SO part of SOHCAHTOA. And that equals the negative 589.286. I have to divide by my sine 45. So we have a negative 589.286 divided by sine 45. So I have my AD vector equal negative 833.376. I can use that information and plug it in over here so that I can find AB. My vector AB plus negative 833 cosine 45. Alright. I do need to discuss this with you because this number ended up being negative. That means I assumed my arrow was in the wrong direction. Or I assumed my arrow and I was wrong. So because that's negative, I'm not actually going away from A. Let me switch up my marker here. I'm actually going towards the joint. Nope, that's not showing up. Yeah, I've got a red Sharpie here. I'm going towards my joint. This is the direction it's actually going. So instead of using my negative 833, because this number was negative 833, this is in my x-axis. In which direction is this arrow going? It's going to the left. Vectors going to the left are considered negative in my x-axis. So just keep that in mind. Solve all of this, and you have to move it to the other side. And your vector AB ends up equaling 589.29. Oh, I actually should check that. My answer key doesn't go out to the thousandths. 833.376 times cosine 45. And that is actually an 8.6. Now I have both of these vectors. I suggest we update this paper. So I know that this right in here is going to be AB 589.286. That number was positive, so I was correct in assuming that they left the joints. So if I'm leaving this joint, I'm leaving joint B, and I'm meeting up in the middle. AD was 833.376. That one was assumed wrong, so that arrow goes towards the joint on both ends. And look at that, I've got a little bit of information. Now let's squeeze over to C. The reason I started with A is I knew a lot about it. I had two forces, one in my X and one in my Y. That's kind of handy. And I knew the dimensions everywhere. So I knew my angle. I then go over to joint C, because again, I have a piece of information. I have a reaction force there, and there's not a lot else going on. Compared to maybe up here at E, I know one force, but there's still three members I don't know. So we're going to go to C. Joint C. This one is stuff going to the left and up. Those are my senses for my two vectors there. My reaction at C in my y-axis is a 535.714. My angle here, same as the last one, it's still 45. So now I have to find all the forces in my X. Oh, sorry, this joint here is C. There we go. So I have C to B. That is strictly in my X, so I don't have to specify. Then I have the X component of C to E. C to E in the X component of it. And those are the only two things in my X-axis equal to 0. My Y-axis, I also only have two. I have my reaction at joint C in my Y-axis, and I have C, E in my Y-axis. Similar to last time, I'm just going to take this triangle, paste it down here for a second. Again, I'm not an artist. Here's C, B, E, 45. Alright, here is the vector CE. Over here is going to be my force in my Y. And here's my force in my X. To find the force in the X, I'm going to use cosine. Cosine of 45 is going to equal k adjacent over hypotenuse. Force in my X over my important vector, the overall vector. So my force in my x-axis, I should label this correctly here, CE in my x-axis is equal to the overall CE times cosine 45. And similarly for the y force, I would switch this out with sine. So I'm going to substitute that up top, leaving CB alone, and that's going to be plus the overall vector times cosine 45. And I don't know either of those, so I've got to hop over to my y side. My reaction at y is 500 35.714. And I am adding that. I'm going to use the important vector and then sine of 45. And I can solve for CE. So I subtract my 535 over. So that's negative 535.714. And I divide by sine 45. Negative 535.714 divided by sine 45. And I end up with my vector CE being negative 757.614. That number was negative, so what's that mean? Something important for sure. It means that I drew my arrow in the wrong way. CE doesn't actually go out, but it comes in towards my joint. Which means this is under compression. I'm under compression. So I take that over here. I still have CB. Keep in mind, CB is going to the left, so I should actually have a negative here. Since CB is going in the left direction, I'm assuming that, because I'm assuming it's going to leave the joint, then these should be negative forces. So I have negative CB plus, and since CE, this one is going towards the right, it's a positive force still. Positive 757.614 times cosine 45 equals 0. 757.614 cosine 45 gets me 535.7. 535.714. I'm going to add my CB over, that way it's no longer negative. So 535.714 equals CB. CB 735, good. So that's one more down. And because this force ends up being positive, I assumed correctly that this arrow was going towards the left. So let's fill out our chart again. Alright. I now know that CB, this one here, is a 535.714. I assumed correctly that it was leaving my joint. This member up here is 757.614. I assumed incorrectly because I ended up getting that negative number. Since I got a negative number, instead of leaving the joint, I'm actually coming towards it, so it's under compression. So I'm going to draw arrows towards my joints. That's quite a bit of our truss. If you notice there, we've only got a couple members we don't know about anymore. We have B to D, B to E, and E to D. What I would do here is I would go up to joint E. I have two members I don't know, but I have two forces I do know. And we're at a half hour. I'm going to leave it at that. But these are my first two joints I would do. That's the next one. So again, we're going to start up the same way. I'll do a little bit of this one. We'll set this one up and then we'll walk away from it. This is what I draw before we got started. And we figured out that this one doesn't go in that direction. CE is actually going towards the joint, and that's all we know that's there that's been changed. It's coming up with a force of 757.614. I have my angles. This one in here is a 45. So I know that this external angle, if you want to think about that one, is 45. And we will have to find this little angle, so I guess I should show that one, huh? That angle if I were to draw it straight down, we are 10 tall, and looking back at our original, where did I put him at? Here. Down to here, we are up 10, and we are over 7.5, and that's going to be that top angle, 7.5. So we use tangent of theta, TOA, this is the one we're curious about, opposite over adjacent, 7.5 over 10. Arctangent, 7.5 over 10. Theta is 36.870. So this angle is 36.8, and I can't fit it all in there, 36.870. Right in there. So that tells me what the rest of that is. 90 minus 36.870, and that is a 53.130. Alright, I have all my angles, perfect. The sum of my forces and my x must equal 0. I have the vector e to d. That's regular e to d. There's no x and y component of that. I have the x component of this vector. If I reference my x-axis, so if I'm using this angle up here, I can still use cosine for my x's. Same thing over here. That's why I like to reference this horizontal axis. So this one, I'm going to the left. Okay, see how that arrow is going up and to the left, so that's a negative in my x-axis. Negative cosine of my angle times my force, 757.614. Same thing with this one. I'm assuming going down and to the right, so I'm assuming it's like a negative force on my x-axis. So I'm assuming it's negative, and this is going to be e to b cosine, and I'm going to use the angle that's referencing to my x-axis, this horizontal axis, 53.130, and all of that has to equal 0. If you notice, two variables, I've got to leave it for a little while, and I've got to come back. Some of my forces in my y-axis must also equal 0. I have the 375 coming straight down, so it's going to be a minus 375. This piece is going to have a y component, and it's going to be negative because I'm assuming it's going down. The e to b vector, and this time sine of 53.130. I have this I have the y value of this vector. This one I'm assuming is going up, so it's going to be a positive 757.614 times sine of 45. Again, I'm using this 45 up here, referencing my x-axis. So we think about this vector over here. This was e to b. Here's my e to b vector. Here's the x component and the y component. Using trig, you figure out that sine, oh, sorry, we're actually using that angle out there. So we're coming over and down that way. Nope, that doesn't quite work there. Sorry about that. We're coming here, over, and down. This is a 53-degree angle. Here is EB, x component, y component. Cosine up here, if I write so, ka, adjacent over hypotenuse. So we're looking back up here now. My x component of EB is adjacent, so my x component over my hypotenuse. That's how we ended up with using cosine of 53. Down here for sine of 53. Sine of 53 degrees equals opposite, or my EB, my y-axis, over, oh, sorry, I switched that up. My opposite value, opposite is 53 is y, so EB, my y-axis, over the whole EB vector, opposite over hypotenuse. Sine of my angle equals opposite over hypotenuse. That's important because I care about the hypotenuse. I don't care about the y component. I just need to use it for a little while. That's a number. That's a number. That's a number. All of that must add up to equal 0. So my overall variable is EB. So I'm going to combine squiggle with squiggle. Negative 375 plus 757.614 sine 45. I have 0 equals 160.732 minus the vector EB sine 53.130. So I subtract this over and I divide by the negative sine 53.130. So if I subtract that over, it's now negative. So I have negative that answer. And then I have to divide by a negative sine 53.130. 0.130. I get the EB 200.916. I know that sounds like a lot, but all I'm doing here is adding up the forces in my y-axis. 2 of them are vectors that come in at an angle. Okay, both of these, EB has a y component, and this one is CE, its y component. I'll write that up here. EB in the y, and this is EC in the y. Since I'm doing y's, I have sines. That's as true as long as I continue to reference my x-axis, this horizontal axis. Up top, I have these 3 vectors. ED, it's already just horizontal. This is the 757, so that's EC in my x, and this is EB in my x. Since I'm referencing my x-axis, I use my cosines of those angles. Now that I have EB, I can spub that in up here. It's a 200.916. Since I got a positive number, I assumed my arrow correctly. So I know EB as in Beatrice is 200.916. So 0 equals my ED vector minus cosine 45 times 757.614. And then I'm subtracting, because of the direction the arrow is going, it's going down and to the left. So that's minus 200.916 cosine 53.130 negative 656 . minus 656.264. Alright, here, listen up to this one. I made a little mistake. ED, which direction is it traveling in? It's going to the left. What are vectors going to the left? They're negative. So that should be negative, that should be negative. Now we should work out. Now I add my 656 over to the other side. Positive 656.264 equals a negative ED vector. So my ED vector equals a negative 656.264. What does that say about our picture? Well, that says our direction for our arrow was assumed incorrect. So ED must actually go towards the joint. Now let's update our overall chart. Our overall chart says this must be going that way, with 757.614, we'll call it pounds. I found out E to B is going, or is in tension, so it's going towards the center. It's in 200.916. And you'll notice I only have one more question mark. That one right there. So it's up to you which joint you want to use to solve for that one. If you use B, you have 1, 2, 3, 4 beams and this cute little force. If you go up to D, you only have 1, 2, 3 beams and this little force. So I suggest you go to joint D from here, but you now have a lot of information for this truss. I think that was good. I think that worked out pretty well. This is a long video, 43 minutes almost. But this is good, and it takes a long time. I'm going slow. I'm trying to check myself as I go. That's understandable. That's something you should do. You should make sure you check this stuff as often as possible. That's why for my students, when I give them these, I give them this cute little paper that has, let me zoom out a little bit. There we go. It has all of the external forces acting on it, and it has all of the forces acting on each member. I give them each of those. So this is what your overall answer should be when you're done. That looks a little unclear. I don't know if I can make it any better. I'll just make it worse. But this is the information I give them so they can check themselves as they go. If you make a mistake here when you're doing joint A, then that's going to screw you up when you start getting over here and up here into these things where it starts to matter what, well, I guess that one it wouldn't. But when you start, you find this one, that now changes what you're doing at joint D to find this force. So check yourself as you go. If you're one of my students, I hope this helps you. If you're not one of my students, please leave a comment below to see what I could maybe do to be better. But I hope this was helpful. This is solving trusses, and this is for POE, or Principles of Engineering, and this is a PLTW, or Project Lead the Way class. I hope this was helpful, and I hope you learned something. Here's my overall truss one more time. I really suggest you break it down piece by piece. I show my students to go through the steps. Step 1 being to just draw the picture. Step 2 to be checking if it's statically determinate. Step 3 is to solve for your external forces. That's external x's, y's, and then of course you have to find your moments. Your moments will help you find usually this force over here at C. Once you have done that, make sure you find out some of your important angles. I would do A and B, or sorry, A and C for sure, because you definitely have to start with those. And then I sometimes, like you saw today, I find my other angles as I go, just so I can hop into the problem. And once you do that, you move into each of your joints. Start off with the one you know the most information about. That's joint A. Once you have found joint A, I would hop over to the next one you have the most information about. That's joint C most of the time, because that's where your other your other roller connection is. You have a reaction force there. And then continue working your way around. You shouldn't have to solve for B, because once you get to D, you'll find this missing beam, and you know all of them now. So that's kind of the fun thing. Sometimes there's one you don't have to solve for. So this one, there's 4 little baby trig problems inside the truss problem. Again, I hope that was helpful. Sorry it's a 45-minute video. I couldn't think of a way to trim that out. Have a good night, everybody. Bye.